Another component to be aware of are the CPU registers. Registers are small, high-speed storage elements embedded directly within the CPU core. They hold operands, addresses, control information, and results used in the execution of instructions. Unlike cache, which store blocks of memory for reuse, registers hold individual values, making them the CPU's fastest accessible storage, closest to the execution units. There are numerous reasons cybersecurity professionals should care about knowing what registers are. Registers are central to instruction-level execution. It's crucial for understanding shell code, syscall interfaces, reverse engineering, and vulnerability exploitation. Additionally, we have privilege separation. Register access behavior differs between user and kernel modes, and side channel vectors. Registers may leak sensitive data through timing attacks, speculative execution, and debugging residue. Understanding register behavior enables professionals to more accurately analyze exploit behavior, mitigate low-level vulnerabilities, and perform advanced forensics or malware analyses. CPU registers are functionally specialized to optimize performance and execution pipeline organization. The main categories, I'm going to list 4. You have GPRs, general purpose registers, SPRs, special purpose registers, SIMD vector registers, and segment and descriptor registers. So the general purpose registers, the GPRs, that's operand storage for arithmetic, logical operations, and memory offsets. The SPRs, special purpose registers, track control flow, status flags, and stack behavior. The SIMD vector registers enable data parallel instructions like AVX and SSE. Now, SIMD stands for single instruction, multiple data. It allows a single CPU instruction to operate on multiple data elements in parallel rather than one at a time. It's ideal for data parallel workloads like image processing, encryption, or multimedia. And SSE, that's streaming SIMD extensions. And AVX is advanced vector extensions. These are Intel SIMD instruction sets. SSE, think of 128-bit wide registers, supporting parallel operations on 4x32-bit floats or 2x64-bit floats. A float is short for floating point number. That's a way of representing real, non-integer numbers in computing that supports fractions, decimal points, and very large or small values by using scientific notation. So a 32-bit float, a 1-bit sign, positive or negative, 8 bits exponent controls a scale or range, 23 bits, mantissa, significand, controlling the precision. Both mantissa and significand refer to the part of a floating point number that contains the significant digits of the number. For example, if we write the number 6.022 times 10 to the 23rd power, Avogadro's number, that fundamental constant in chemistry and physics, that 6.022 is the significand, also historically called the mantissa, and the 10 to the 23rd power is the base raised to an exponent. So mantissa is historically used but technically incorrect. In mathematics, the mantissa is the fractional part of a logarithm. In modern computer architecture, significand is the correct term for the digit carrying part of the float. So it determines how many meaningful digits the float can represent. And then the AVX is that, let's say, 256-bit AVX and 512-bit AVX-512 wide registers allow that wider parallelism and newer instructions. So the SIMD registers let CPUs process multiple data items in parallel using one instruction, dramatically speeding up vectorized operations in fields like cryptography, graphics, and scientific computing. And then fourth, we have that segment and descriptor registers. Those are used for memory protection and privilege separation in x86 systems. So the general purpose registers, they're for operand storage, for ALU operations, and for function call argument passing per calling convention. And that's talking about how function arguments or parameters are passed into functions at the machine level using specific CPU registers. And the rules for doing this are governed by something called a calling convention. A calling convention defines how functions are called at the assembly level, including how arguments are passed in registers or on the stack, which registers are preserved across function calls, and how the return value is delivered. So when a function is called in code, the first few arguments are placed directly into general purpose registers, depending on the platform and calling convention. And the registers used for arguments do vary by OS, operating system, and architecture. It can be helpful to understand things like these different ways that the x86-64 Linux, System V AMD 64 ABI work versus the x86-64 Windows, like Microsoft x64 calling conventions, and the x86-32 on both platforms that almost always passes all arguments on the stack, not in registers. It can be helpful to understand these if you go into this area of cybersecurity, because these rules tell you how you should prepare a function call at the assembly level. So if you're writing shell code, if you're reverse engineering function calls in disassembly, if you're working on exploit development like ROP chains, and an ROP chain, that stands for Return-Oriented Programming, which is a powerful exploit technique used to execute arbitrary code without injecting new code. By chaining together existing instructions, referred to as gadgets, already present in a program's memory. The basic idea of it is, let's say an attacker can't inject new code due to various protections, so instead, they reuse small sequences of instructions, perhaps that end in a RET, return. These are called ROP gadgets. By carefully arranging return addresses on the stack, the attacker tricks the CPU into executing these gadgets in a controlled order. This chain of gadgets is equal to the ROP chain. Each gadget usually does a very small operation, just a tiny little thing. So suppose a vulnerable buffer allows a stack overflow. The attacker might overwrite the return address to point to a gadget, place a value on the stack that gets popped in. Next return address points to another gadget, chains of many of these gadgets to build arbitrary behavior. And eventually the chain might do things like set up a syscall, disable memory protections, load shellcode from somewhere else. ROP is definitely important in cybersecurity because it bypasses some of these data execution prevention protections and various other built-in security mechanisms, since ROP doesn't inject the code, just reuses what's already mapped in the memory. And it's often used in things like privilege escalation, remote code execution, and bypassing sandbox protections. So the modern defenses like ASLR, stack canaries, and control flow enforcement are trying to make that ROP more difficult. So you can think of ROP as building a program using scraps of someone else's program, carefully arranging it so that each scrap runs in the sequence the way that you want it to. So further on the security relevance of understanding these general purpose registers, they're used in shellcode payloads and ROP chains, and they function as syscall argument holders in Linux and Windows. Now, a syscall is short for system call. That's a mechanism allowing user space programs, like your browser, your terminal, or any app, to request services from the operating system's kernel safely and in a controlled way. You've got common examples like your read, write, open, map, things reading data from a file or socket, writing data to a file or socket, executing a new program with execve, opening files and mapping memory. So in essence, a syscall is the controlled interface between unprivileged code and privileged kernel functionality. A syscall argument is that input value, as every syscall requires these input values, and these are the arguments to the syscall. So the write function perhaps might have buffer and a pointer to data to write, the FD for the file descriptor, the length meaning the number of bytes to write, and these arguments have to be passed to the kernel when that syscall is invoked, and this is where the registers come in. A syscall argument holder is just a register that temporarily holds one of the arguments passed into a syscall. Before calling a syscall, a program has to load each argument into the correct GPR, general purpose register. The syscall number, that tells the kernel which syscall you're invoking, and after placing arguments in GPRs, the syscall instruction is executed. Good to know. For the exploit development, attackers use these general purpose registers to set up fake syscalls in ROP chains or shellcode. And reverse engineering, understanding GPRs lets you trace syscall behavior from assembly. And then hardening. Malicious use of syscalls is often at the core of malware, like invoking that execution call to spawn a shell. And then for the security relevance of GPRs, we also have the volatile and non-volatile status affects exploit developments, like stack pivots and return values. And a stack pivot is when an attacker changes the stack pointer to point somewhere else, usually a controlled memory area, so they can take control of program execution. Because, as we noted, the ROP chains are built on the stack. If you control memory like a buffer, but the real stack pointer isn't pointing to it, your ROP chain won't run. So attackers use that stack pivot gadget to redirect the pointer to their controlled data. General purpose registers matter here because you often load the target address into a GPR and then pivot using a gadget. And I mentioned return values in assembly and syscalls. The return value of a function or syscall is placed in a specific GPR. So that return value would be placed in that specific general purpose register. In exploits, this is important when you want to use the return value in a follow-up step, like a file descriptor or a memory address, or when you're building a chain where one gadget depends on the result of a previous syscall function. And then we have the type of register that SPR, the special purpose registers. There's, for example, the instruction pointer that tracks the address of the next instruction, the stack pointer pointing to the top of the stack, and of course the stack is that special region of memory used by programs to store temporary data, like the function call information, the local variables, return addresses, and saved register values, working like a last in, first out structure, LIFO. The last thing pushed onto the stack is the first thing popped off. The stack pointer points to the top of the stack. When a function is called, the return address is pushed onto the stack and space is allocated for local variables. When the function returns, the stack is popped to restore the return address and previous state. And stack overflows can overwrite return addresses, control flow hijacking. ROP chains are usually placed on the stack, and the stack is central to most memory corruption exploits. So then another example in association with the SPRs, the special purpose registers, is the base pointer, and that defines the current stack frame. And then we have the status register with flags like 0, sign, carry, overflow, interrupt enable, and direction flag for a few examples. The purpose of the special purpose registers, the SPRs, is to manage control flow and processor state. It's used in exceptions, interrupts, conditional branches, and procedure calls. There are the security relevance portions like stack pivoting via the pointer, branch logic manipulation through conditional flag abuse, and the EIP RIP control is the goal of most control flow hijacks. So EIP is that extended instruction pointer used in 32-bit x86 systems, and the RIP is the register instruction pointer used in 64-bit x86 64 systems. Both registers hold the memory address of the next instruction the CPU will execute. The CPU reads the instruction at the address in EIP-RIP. After executing, it automatically updates EIP-RIP to point to the next instruction. You can't directly write to RIP as it's updated through those control flow instructions. So in other words, if you can control RIP, you can make the CPU execute instructions at an address you choose, such as an ROP chain on the stack, shellcode in memory, a known function in a library. And most memory corruption vulnerabilities like buffer overflows, use after free, and stack overflows, for example, are exploited with the one core goal of diverting program execution to attacker-controlled code. And to do that, it helps to control the instruction pointer. People commonly achieve RIP control with stack buffer overflow, overwriting the saved return address on the stack, with function pointer overwrite, corrupting a pointer used for indirect calls, with the ROP chains, as we mentioned many times here, redirecting RIP to the start of a chain of gadgets, and with use after free. By freeing an object, reallocate it with attacker data and overwrite function pointers or vtables. So it's definitively got security implications. Controlling RIP is controlling the program. Defenses like DEP-NX, ASLR, stack canaries, and control flow integrity, CFI, exist specifically to prevent or detect this, and exploit writers often build entire chains of payloads around achieving RIP control. So considering register files and architectural versus physical registers. A register file is a hardware block that stores all visible architectural registers. Architectural registers are the registers defined by the ISA. The ISA stands for Instruction Set Architecture. We'll be going a lot more into this in future videos coming up shortly, but that's the interface between software and hardware. It's a specification that defines a set of instructions the CPU can execute. It defines the registers available and the data types, memory addressing modes, and interrupt handling rules. In simple terms, the ISA is the language the CPU understands that compilers target. We've got examples of ISAs for x86, the 32-bit Intel AMD instruction set, the x86-64 or AMD 64, 64-bit version of x86, ARM, used in most smartphones and embedded devices, and RISC-V open source ISA, instruction set architecture, that's been gaining popularity. All of this matters as architectural registers are defined by the ISA. Software compiled for a CPU must match its ISA, and low-level security analysts, reverse engineering, shell code writing requires understanding the ISA. And then the physical registers are the actual hardware-backed storage units that are dynamically assigned. There's register renaming, which is done in out-of-order execution CPUs to avoid false dependencies, managed by the register alias table, RAT, and reorder buffer, ROB, and increases performance but complicates runtime visibility. Our security relevance renaming obfuscates actual data flow during speculative or side channel analyses, and it makes forensic analyses at runtime, like live debugging, more complex. We have register use in instruction execution. So the example of add EAX and EBX adds the contents of EBX to EAX and stores the results in EAX. Got a register to register instructions execute without accessing memory. And registers reduce latency and instruction cycles that's critical in tight loops or performance-sensitive code. So Registers, they operate at clock speed, but there are nuanced technical realities. So registers reside in the CPU core and are implemented using flip-flops or fast SRAM-like latches. Both flip-flops and latches are fundamental digital storage elements used in CPU and memory design to store one bit of data, 0 or 1. They're the building blocks of registers, counters, and state machines in digital circuits. A flip-flop is an edge-triggered storage device. It captures and stores a bit of data on a clock edge, usually the rising edge of a clock signal. Once triggered, the output holds its value until the next clock edge. It can be synchronous, responding only at specific clock transitions, like the rising edge of the CPU clock, and used when precise timing is critical, like in CPU pipelines or instruction registers. So think about this as flip-flops wait for the clock to tick before updating. And a latch is a level-sensitive storage element. It stores data as long as an enable control signal is active, like when a gate is open. It can be transparent, immediately passes input to output when enabled. Is the characteristics of being asynchronous and level sensitive, as mentioned, and updates as long as the control line is active. It's more power efficient and faster in some designs, but can cause timing issues in high-speed synchronous systems. Latches are like doors that stay open while enabled, letting data flow through. And CPU registers are built using arrays of flip-flops or latch-based structures, depending on performance, area, and power trade-offs. Most modern CPUs use edge-triggered flip-flops for core registers to maintain precise control in high-speed clocked environments. Some register files, like in GPUs or vector units, may use SRAM-like latch banks for efficiency. So registers operate in clock speed, and these nuanced technical realities also include that they're fully synchronous, and they operate in the same clock domain as the execution units. Access latency is 1 clock cycle or less. That's that raw electrical access. And register reads and writes occur at CPU clock frequency, making them the fastest accessible elements in the memory hierarchy. And in pipelined architectures, register reads and writes are typically aligned to specific pipeline stages, like decode and execute. Forwarding and bypassing logic handles data hazards, and delays may occur due to stalls, hazards, or instruction dependencies. Therefore, although register access is clock-aligned, data availability might not be immediate due to pipeline scheduling. And just a quick understanding, a pipelined architecture is a CPU design that breaks instruction execution into multiple stages where different instructions are processed simultaneously at different steps, like an assembly line. Your typical stages are fetch. Number 1, get the instruction from memory. Number 2, decode, figure out what the instruction does. Number 3, execute, perform the operation, like adding or multiplying. Number 4, memory, access RAM if needed. And then write back, storing the result in a register. And this pipelining improves performance by increasing instruction throughput, as multiple instructions can be in flight at once at each different stage. And register reads and writes must happen at the correct stage, like read and decode and write back. Pipelining introduces challenges like the data hazards, which require forwarding or stalling to ensure correctness, though. When we compare to cache, we have the L1 cache, 3 to 5 cycles latency on modern CPUs. Registers would be less than or equal to 1 cycle latency, but subject to the pipeline constraints. So registers are faster than any cache level in real and effective access time. For out-of-order execution and register renaming, CPUs dynamically map architectural registers to physical ones. The RAT, Register Allocation Table, maintains the mappings. And this indirection allows parallel execution, but can obscure which physical register is read or written at runtime. Timing and access paths are still fast, but the behavior becomes less transparent. So registers operate at CPU clock speed, but due to pipelining, out-of-order logic, and hazards, actual instruction timing might involve some subtle delays. So there are a lot of security implications, as you are now aware, of these registers. And just to go into that a little bit more, we've got the residual data leakage. Register content may persist after context switches, syscall exits, and process termination. So that content might still be there. It might persist. And sensitive data, like keys, tokens, credentials, they could remain unless registers are explicitly zeroed. Well, speculative execution and side channels. Throughout this course, you're hearing that a lot. Spectre meltdown attacks exploit speculative reads. In this case, we're talking about they exploit these speculative reads from registers. And registers contribute to cache timing artifacts exploited by these exploits: flush plus reload, prime plus probe, port contention side channels like register contention and simultaneous multithreading. And for forensics and reverse engineering, you have debuggers that expose those live register states. Malware might use register rotation or opaque predicates to evade static detection, and malware might leak secrets via misused system calls or exception handling. And ROP, return-oriented programming payloads, do heavily manipulate register state. They can. So it was good to get a little bit of an understanding of what registers are and how they are foundational to CPU operation. They serve as the fastest storage elements accessible to the processor. They're executed in every instruction cycle and are tightly coupled with instruction decoding and execution. And they play a central role in security, from vulnerability vectors to analysis tools. Understanding registers bridges this architectural and operational understanding that's very helpful for cybersecurity professionals, particularly those working in exploit development and defense, in secure software engineering, in reverse engineering, and in malware behavior analyses.